Hi, this is Narayan from Shastra Deemed University, Tanjavur. This is a part 2 video on fluidization as part of the unit on fixed and fluidized bed. This is for the course on fluid mechanics CHE 105 for the chemical engineering second year students. So, if you have seen the part 1 video, we discussed about the profile about pressure drop versus flow rate for a fixed bed. Then we said we will remove the top plate. Then we discussed about what happens to the pressure drop versus flow rate or the velocity profile in terms of unfluidized bed. Then we said that the experimental evidence suggests that there is a transition occurring. So the pressure drop increases with increase in velocity for one range, which is like the bed range, fixed bed range A. Then afterwards the pressure drop remains constant, which we call it as a fluidized state. So the bed, if your flow rate is in this part, then the bed is says to be in fixed bed mode. If your flow rate is greater than this transition part, then we call it as the bed to be in the fluidized bed mode. So that means that any conditions more than this transition point, the bed is in fluidized. So in this video, we'll talk about how to find this transition velocity given the fluid particle systems. So let me again take this graph. So this is how the graph of a pressure drop versus, like, say, this could be superficial velocity typically, but this can also be like flow rate or mass flow rate of the fluid stream looks like. So in the region A, so the pressure drop increases with increase in velocity, and once the bed has attained the fluidized state, the pressure drop remains constant. So we want to find out this point where the pressure drop starts to equalize. So that means where the bed goes from fixed bed to fluidized bed, this point is called the transition point, and we are indicating that transition velocity as UMF. U stands for velocity and MF stands for minimum fluidization. So that means the minimum velocity that is required for the fluid if the bed has to be in the fluidized bed state. Now let's do some high school maths, that's all. So we want to find out this point, which eventually means this point can be thought as the point of intersection of two curves or two lines, as you see here. So the line 1 and the line 2. So that means if I have an equation for line 1 and if I have the equation for line 2, so, and this point, so which is the UMF point, satisfies both line 1 and line 2, right? So I again repeat, so if we have an equation for this pressure drop in terms of velocity as per line 1, and we have another equation for pressure drop, which is again in the y-axis with respect to the x-axis, which is here velocity for this line 2, that means at this point of UMF both these lines intersect. So that means UMF will satisfy the equation of line 1 and it will also satisfy the equation of line 2. So that's what I have written. So suppose let us have delta P, if we can write as function of velocity, this is for the line 1, and suppose if I can write an expression of pressure drop for the line 2, that means at the intersection point both these pressure drops are same. So that means at this U equal to UMF, you will get the same value of pressure drop whether you compute by line 1 or you compute by line 2. So that's what mathematics says. So let's see what is the equation for line 1 and line 2. Line 1, which is primarily the pressure drop in the region 1 or the region A, which is a fixed bed region. We know that pressure drop, the frictional pressure drop rather, is given by the Ergun equation. So that means if all the fluid flow energy, all the velocity that is given by the fluid is to overcome the frictional pressure drop. Now remember, pressure drop is analogous to the power that is being consumed, that is being required for the fluid, because power consumed is pressure drop times the volumetric flow rate. So that means for the region A, where or the line 1, you know the pressure drop is given by this Ergun equation. Now what happens in the line 2? Now I hope you have seen the video on fluidized bed. So it's not only this graph, but you know that in the fluidized bed region, so that means in the line B, there's a continuous increase in the bed height. So what do you mean by continuous increase in the bed height? So the distance between the particles keeps on increasing, and you have a taller and taller bed. Let me show this by a sketch, maybe for a good representation. I'll just put on the video and slightly arrange for this text. So that means, let us say this is a bed. This is a bed, and this is, let's say, the distributor plate is here, right? And let's say this is the initial height of the bed. It's not continuous, so it's just particles are there. So I'm just describing it by this shaded part. So you have a fluid being sent. Now, as long as your velocity is less than the minimum fluidization velocity, this height, what you see in this first diagram, will always remain same. So that means your H will remain invariant, will not change as long as you obey this condition, and this is what is called the fixed bed state. Now suppose if your velocity is greater than UMF, so take points which is greater than UMF. Let us take two velocities U1 and U2, both of which are greater than UMF, and let us say that U1 is less than U2. So we are considering another state here, another two operating conditions, let's say U1 and U2. Both of these velocities are beyond the transition point, and U1 is actually slightly lesser than this U2. And what will happen is you have the same bed. So you have the same bed. So this is at U1 state, and this is at like U2 state, right? You still have the distributor plate here. So let's have the distributor plate here. But now this bed will be at little higher position. So these particles would have got expanded, and here it is even more, this would have got expanded. So that means if this is let's say this H naught, which is the initial bed height at the fixed bed. Now this is, like, say, H1, and this is, like, say, H2. So H naught is the height of the bed at a fixed bed condition, and let's say H1 is the height of the bed at U1, and U1 is greater than UMF. So U1 is all these are average velocities or the superficial velocities based on empty cross section area of the bed. So that's why I just want to put U bar. So that means all these velocities are the superficial velocities. That means flow rate divided by the empty cross section area of the bed. So this height H1 is the height of the bed at when the operating flow rate is U1. U1 is also greater than UMF, and H2 is the height of bed at U2 bar, and U2 bar is also greater than U1 bar, so obviously this is also greater than UMF. You see that as your velocity increases, so that means as you increase your velocity greater than UMF, your height of the bed also increases. We are not adding extra solid particles, we are not pouring in anything, there is no excess, so there is no particle addition. So that means how this particle height increases, that means we just think for a moment, it should be obvious. So can the particles grow? So is it like, for example, in this state the particle size is here, and as the velocities increases the particles become bigger? Now this is also not possible. So that means it is not particle growth, no particles are added, no particle growth. So that means the particles are not growing in size, it is not taking in gas to becoming bigger. So then the only possibility that we have is the interstitial spaces between the particles increases. So that means interstitial space will increase as more and more gases pass through this. So that means as more and more fluid is sent, so the distance between the particle increases. So the distance between the particle increases, eventually for the same cross-sectional area of the bed, the height increases, right? So that means now as you increase the velocity here, so that means you are putting in more kinetic energy, all this energy is used now to lift these particles up. So that means they are used to move this bed higher and higher. So that means they are moved to increase the interstitial spaces eventually. So that means these particles are not falling down. So right, so when the gas is continuously pumped inside, these particles don't settle. So that means the gas or the liquid, or in general the fluid, supports the weight of the bed, or rather this fluid flow, upflow, or the drag of the fluid up flowing upward. So that means the force due to the fluid that is flowing upward balances the net weight of this bed. Is it clear? It balances the net weight of the bed. So let me come back to the PDF. Yeah. So that means in the second part, so that means the equation for the second part, all the fluid energy, all the fluid that's flowing through supports the net weight of the bed. So that means the drag force per unit area, which is again eventually the pressure, is equivalent to so the drag force per unit area, which is the pressure of this static bed, of this bed that is supported by this upflowing fluid, is just equal to the net weight of the bed. And so that's given by this expression. We know, right, P is equal to H rho G, so it is symbolic in the same form. Delta P is equal to delta rho into epsilon plus G into L. L stands here for this height of the bed or length of the bed at that given condition. So that means this L is not the bed at the fixed bed condition. So this L is not this height, L is not this initial height, L depends on what velocity we are talking of. So that means L is for a given velocity. So that means L is now a function of u itself. Is it clear? And why here we have written epsilon Sg? Because we have accounted only for the weight of the particles in the bed. We have neglected for the buoyancy effect, and that is why it is delta rho into epsilon Sg. Delta rho stands for rho of the particle minus rho of the fluid. It could be rho of the liquid or rho of the gas. So delta rho stands for rho p minus rho. Epsilon s stands for the net volume that is being occupied by the solid. So together it stands for the net weight. So now we have already seen, so this transition point is satisfied by when these two curves meet. So that means these two expressions should be the same. So that means the pressure calculated by the Ergun equation and the pressure drop calculated by this net weight, both should be same at this point of transition. We have divided by the gradient L because in both this equation you have L, and L is going to remain same at this point. So that means the same value of L is taken for region A and region B at the point of intersection. So that means pressure drop gradient at the transition point, which is given by the Ergun equation, should also be equivalent to this net weight of the bed. Now if you carefully see these terms, this looks like a quadratic expression in terms of UMF. So we will only focus on this term. So that means this looks like as if it is A UMF square plus B UMF plus C, where A is this part, which is the coefficients of the square of the velocity term, and B is actually this part, so which is the coefficient of the linear term in velocity. And you obviously have here C. Here C, I am not focusing on this part, I am focusing on this part. Note C is on this side, so you will have it as a negative. So that means, let me again go back to the video probably to make it a little more clear. Let me take the next page. So that means the point of transition is given by an expression AUMF square plus BUMF plus C equal to 0, where A is 1.75 rho epsilon S by, this is evaluated at minimum fluidization condition, pi into dp into epsilon. Again, epsilon is evaluated at minimum fluidization condition, the whole cube. B is 150 mu, again epsilon solid holdup, evaluated at the minimum fluidization condition, into phi square dp square epsilon. Voidage fraction is again at the minimum fluidization condition, and C is minus delta rho into epsilon S mfg. Delta rho is rho minus rho b. So this is a quadratic equation. If you know all particle properties, so if you know the particle property, you primarily know phi and dp. So if you know the fluid property, you know rho and viscosity. So you need to know the voidage fraction at a minimum fluidization condition, which is typically given or is an experimental parameter, or we can have a nominal value assumption for this. So that means if all these are known, then one can solve this equation and get the roots. So it can have two roots. Of these, only one of the roots would have been the positive value, which will indicate the minimum fluidization velocity. So that means it is indeed possible to calculate this transition UMF knowing the particle properties, fluid properties, and by an experimental or assumed value of minimum fluidization voidage. So this minimum fluidization voidage is not equivalent to the voidage of a fixed bed. Now this is easier to define why this should not be the same, because at the point of fluidization, the fluid particles have already started to disengage from oneself. So that means you have interstitial space is more at fluidization. Alright, interstitial space is more at fluidization. So that means your voidage is not equivalent to the fixed bed voidage. Rather, voidage of minimum fluidization is slightly more than the voidage at the fixed bed, because you have now more spacing. So this is one point that you have to note it down when you are assuming. You cannot assume a voidage which is equivalent to a fixed bed, or you cannot assume a voidage which is less than the fixed bed. Your voidage will be slightly more than the fixed bed voidage. You can look into the textbook for the nominal values. So if you know all of these and then you solve the quadratic equation in terms of UMF, you will get what is the minimum fluidization velocity, and the flow rate corresponding to minimum fluidization can be got from the minimum fluidization velocity times the area of cross section of the bed. Remember, this is on the superficial velocity, so that means we have to calculate based on the cross sectional area of the bed and not the actual velocity. And the mass flow rate of the fluid corresponding to minimum fluidization is the density of this fluid times the volumetric flow rate at the minimum fluidization. So this summarizes how one can get a minimum fluidization velocity or the transition point. Now remember, at any operating velocities which is greater than UMF, the bed is always said to be fluidized or said to be in a fluidized state. So UMF is a state of minimum fluidization. So that means it is that point where the fluidization starts. And at any velocity which is less than the UMF, at any velocities which is less than the UMF, the bed is said to be in a fixed bed state. So if your operating condition is in this part, you are in a fixed bed state. If your operating condition is in this zone, then you are in the fluidized state. So I will end this second part of this video here, and we will see in the next part how to calculate what about the height of the fluidized bed. I said here the height or the length of the fluidized bed, which is you have written here, is also a function of velocity or the space. So let's try to do something with respect to this and see whether can we compute this. So in this second part, all we have done is to arrive at an expression that helps you to calculate minimum fluidization velocity. Thank you for your patience hearing. See you. Bye.